This lecture is being brought to you in part by the generous gifts of these sponsors.
Good evening. Thank you so much for this warm welcome. Thank you, Laurie. It's a real privilege for me to be here. I was visiting IHMC in Pensacola just 10 days ago. And, you know, you have to realize this organization is like has all the attributes of a time machine. You walk in and you are transposed to the future. Okay. What you're seeing at IHMC is work that is essentially looking at how the human being can better its life and also the life of others and the life on our planet in the future in ways, of course, that are ethical, thoughtful, anticipatory. So I'm just a visitor here at IHMC, but those of you who are supporters of its mission, of its cause, I hope you continue to do that because it's an incredible resource and asset for the nation. My dog Apollo sends his regrets. He had other commitments. And tonight we're going to talk about the moon, the good old moon, which of course we see every night, almost, and the good old moon where we are about to return with humans and in particular American astronauts. So this is an amazing time in history. In fact, I'm really optimistic about our future in spite of what you might hear in the evening news sometimes. This is a very special time in our time on the Earth. I think that, of course, we have to proceed cautiously now that we are going to merge humans and machines more and more. But at the same time, I think there's something profoundly amazing about it, which I think in some sense is immortality. Okay? It's going to be very hard for us to achieve immortality biologically, although people are working on it every day. But with the help of machines, we tend to view robots and machines as sort of separate from ourselves these days. But as we progress into the future, we will have androids that look like you and me, that we can create that might even look like our parents or people we've lost, who will have their voice, who might even behave like them. And there's nothing wrong about it, really, when you think about it. And in some sense, they will open huge doors for us in terms of our future in space. We're faced with the daunting prospect of being trapped just where we are here biologically in the solar system. But if you think of an android, a robot that essentially becomes so intelligent that you relate to it as you would to another person, it becomes like the character in Data in Star Trek. You know, when Data goes down, you feel bad, you feel sad. When Data is working, you recharge him, and things are back to normal. My point here is that I think we will relate to robots and machines like we do to offspring. And in a profound sense, they are the offspring of humanity. They are simply a technological future for our biological selves. And we shouldn't be fearful of them. We should be nurturing of them and make sure that we program them with good behavior and ethics. And I say this because interstellar travel is really what's looming. Why do we want to go to the moon? Why do we want to go to Mars? I think it's because there's something out there that we're curious about and we want to be able to access it. Interstellar travel is really a daunting wall for us right now. Just to give you a sense, we live in a galaxy of which the sun is just one star, and the galaxy is a swarm of about 100 billion stars right now. And then, of course, there are hundreds of billions of other galaxies out there beyond our own galaxy. But within our galaxy, within these 100 billion stars, the galaxy spans about 100,000 light years, meaning that if you were traveling at the speed of light, it would take you about 100,000 years to follow a light going from one end to the other end of the galaxy. If you look at a star within our galaxy that's at the other end of the galaxy, you're looking at it the way it was 100,000 years ago, because light that is coming to your eyes or to your telescope from it left that star 100,000 years ago. So we have this immense galaxy that we're embedded in. And if you think that we're very near other stars, you have to consider the following. If the sun were the size of a grapefruit, and you put the grapefruit in, say, San Francisco at the beginning of the Golden Gate Bridge, Pluto at that scale would be a tiny pinhead at the distance of the first pillar of the Golden Gate Bridge. The nearest star, which is a smaller star than the sun is a grapefruit, that star would be the size of a cherry. That cherry would be in Chicago at that scale. So there's a huge gap between Pluto, one of the most distant planets or small planets around us, and the next star. And think of this being typical of the distances between stars in our galaxy. Okay? So we're not ready quite yet for interstellar travel, and I think that ultimately we will achieve it if we manage this transition from a singularly biological humanity to one that is also technological. Anyway, a base at Clavius, why is that a good idea? So this is the moon. You are familiar with the near side of the moon, but there's also the far side, which we never see from the Earth except for the very edges because the moon wobbles a bit. And what I have put on this map are the successful missions and a few crashes, some of them intentional, that have taken place on the moon so far. And the big letters in light blue are the Apollo moon landings, the only human landings ever on the moon so far. And you notice that from Apollo 11 to 12, we skipped 13 because there was an accident, but 14, 15, 16, 17, they're all relatively close to the equator. And that's something that we will think of the implications of in a bit. But there's lots of things going on, and some of the dots here on this chart have not happened yet. There are some upcoming missions. For example, the Blue Ghost mission, one of the two Blue Ghost missions, the Blue Ghost M2 or M1, is on its way to the moon as we speak. China has joined the party, which until then was mostly Soviet Union and the US. China has crashed its first lander on the moon, Chang'e 1, but then landed successfully a rover and a lander at Chang'e 3 site, and then did the same thing on the far side of the moon, Chang'e 4, lander and rover. And then with Chang'e 5, brought back some samples from the near side of the moon, and with Chang'e 6 recently, brought back samples from the far side of the moon, the first samples ever from the far side of the moon. And the far side is interesting, incidentally, because there's a giant ancient impact crater called the South Pole Aitken Basin, and it's one of the most ancient basins that we have a record of at the surface of the moon still. Before we leave this chart, I just want to let you know about one thing, which is that the moon, at least on the near side, presents two main types of terrain. The light-colored terrain is more ancient. It's called the lunar highlands, or the lunar terra, the land of the moon, if you will. And the lunar highlands, which occupy all of the far side almost, and a lot of the near side, are the ancient crust of the moon. Okay, when the moon solidified from being a magma ocean early in its history, it formed a crust, and that is what is today the lunar highlands. And of course, it's very ancient and therefore very heavily cratered because it's been pounded for a long, long time by asteroids and comets. On the near side, you also have a lot of these dark areas. These dark areas are volcanic lava plains. They represent lavas that rose from the inside of the moon and ponded in the largest impact basins. And because the crust of the moon is thinner on the near side, they basically broke the surface and filled in like you would a pond, the near side bowl-shaped depressions of the moon. Okay, now these lavas, these eruptions of volcanic lavas took place over a long time, but they actually post-date the formation of the crust of the moon, and so they have fewer impact craters. All right, and these dark volcanic areas are called the mare, the seas of the moon. Of course, there's no liquid on the moon; it's all seas. It's all solid. All right. Next slide. Okay. The Apollo missions were, of course, amazing. Here are the 9 Apollo missions that actually made it to the moon. 3 just went around the moon, and the 6 others landed. So Apollo 8 just went to the moon to do a sort of flyby and came back. Apollo 10 was a rehearsal for Apollo 11. They could have landed on the moon, but did not, just used the lunar module to come close to the surface and went back up. And then Apollo 11 took place, which was incredible if you lived through that. Apollo 12 was an amazing feat of precision landing. It landed about 200 meters away from a robotic lander on the moon. To think about that, they could have landed on it if they wanted to. They landed just within walking distance of it. Apollo 13 had its mishap. Apollo 14 was led by Alan Shepard, the first American in space. He was, among the Apollo astronauts, one of the least interested in geology. So to meet his quota of rocks, instead of picking up carefully selected little small-sized samples, he just picked up the first giant boulder that he found and loaded it onto the lunar module. And that big rock, I have a picture of it there on the far right, in the middle row. That big rock is known as Big Bertha. And Big Bertha was considered to be a big yawn for most scientists for decades until just 2019. In 2019, it was realized that there was a tiny little fragment that was embedded in this rock from the moon, and this little fragment was not from the moon, but from Earth. And that's because it dates back to a time when the Earth was itself being pounded, like it is still today occasionally, but at the time a lot, by asteroids and comets. And at some point, a little chunk of the Earth got blown off, crash landed onto the moon, got mixed into its soil, and he's eventually rewelded into a rock that was picked up by, of all people, Alan Shepard. And so Big Bertha is turning out to be one of the most incredible samples ever returned from the moon, once again by the least inclined astronaut geologist. That fragment, by the way, is now the oldest dated piece of Earth rock that we know of. It dates back to something like 4.46 billion years in age, to the very beginning of the Earth-Moon's history. Okay. Anyway, Apollo 15, 16, and 17 had the amazing accessory of a rover, and that was an incredible thing as well. But the Apollo missions were fundamentally sortie missions. I mean, they achieved 3 big things, 2 of which are well known by the public. One is that we beat the Soviet Union at something in space. They were ahead, at least on paper, and indeed as well, but not in sort of engineering sophistication necessarily. But nevertheless, they were ahead in the space race. And the Apollo program was an opportunity to do something that was hard enough to do, far enough in the future that we could catch up with it. I mean, the Soviet Union had launched the first satellite, Sputnik, the first living being in space, Laika, the dog, the first man in space, Yuri Gagarin, the first woman in space, Valentina Tereshkova. They did the first spacewalk in space with Alexei Leonov. They did the first rendezvous in space. So enough was enough, and President Kennedy essentially asked, what on earth can we do to beat the Soviet Union in space? And the answer, Mr. President, is to put a man on the moon before the end of this decade and return him safely to the Earth. So going to the moon had nothing to do with science. It's not like in the mid-60s we became interested in moon rocks. It had all to do with showing that our way of life was superior to the Soviet or communist way of life on the other side. And so going to the moon would be hard enough to do, far enough in the future, that we were able to catch up and win the ultimate race and the ultimate prize. So that was the first benefit. The second benefit, really, of course, was science. We learned a lot about the Earth-Moon system. The third thing that's not realized too much is that during the Apollo program, a very narrow window of about 10 years, there was a doubling in US universities of graduates in STEM fields, science, technology, engineering, math. The Apollo program galvanized an entire generation of young people in this country to go into scientific fields. And this actually became the foundation for the high-tech industry that we're still really relying on today for our technological supremacy. So As much as it was a costly program, and you could always argue, why didn't we spend the money on Earth instead of spending it in space? Well, the money was actually spent on Earth. The money was spent in factories, in universities, in education, in new hardware and know-how. It was a formidable investment into the nation. And so that's the third big benefit that we're still reeling on, and it's no surprise that the tech giants of our time are people who were inspired by the Apollo program and have space programs of their own. Anyway, the Apollo missions, however, were short-sighted from a sort of a implementation standpoint. They were what you call sortie missions. There was no aim to set up a base, anything lasting. You go there. It was sort of the luxury buffet approach for scientists. Yeah, let's land here, spend a few days. Okay, we got another mission, let's land here now. Let's land there. There was no thought or budget to think beyond these sortie missions. And that, of course, made it scientifically very exciting and rewarding in the short term, but it also made the program eminently cancelable. And sure enough, that's what happened under the Nixon administration. President Nixon essentially thought that we had won the moon race. There were other things, there were other pressing needs in the nation. And also, we were risking an accident. These Apollo missions were becoming riskier and riskier. And let's pull the plug before this turns against us was sort of the thinking. And so that's why we stopped going to the moon. And at this point, we have just left essentially a junkyard at every one of our Apollo landing sites. I mean, nothing too environmentally damaging, but nothing that we can really build on for the future. And then comes the 1990s. The late 1990s, we discover water ice at the poles of the moon, both the North Pole and the South Pole. And this was an incredible discovery. We realized that at the South Pole and at the North Pole, there are craters, some of them very deep, that never see the light of day. The sunlight never shines into these craters because sun at the poles of the moon is on the horizon, and if you are deep inside the bowl of an impact crater, you're not going to see the disk of the sun. So the insides of these craters are what you call permanently shadowed regions, PSRs. And in a PSR, since you never see the sun and the moon has no atmosphere to even out temperatures, you are going to be subject to temperatures that are close to the surface temperature of Pluto. It's about 50 Kelvin inside these large PSRs. 50 Kelvin is minus 275 degrees Fahrenheit. Okay, minus 370 degrees Fahrenheit. So super cold. And the fact that we discovered water ice at the poles sort of made sense because it looks like these very cold areas that are permanently shadowed, these permanently shadowed regions, were cold enough to cold trap water. So even though the moon is not supposed to have a lot of water because of its history, and most of the water from the moon has been baked out, basically, it seems like every time you have a comet slamming into the moon, which brings in water ice, regardless of where it hits the moon, eventually one molecule at a time, they make their way bouncing around the lunar surface, but over time, one ends up in the polar regions, and then they keep accumulating there because the temperatures are so cold there. So that's a process called cold trapping, and it's believed that what we are seeing here in the polar regions of the moon is not so much ice that has somehow come up from the inside of the moon, but ice that has been brought in by comets and trapped in these cold traps, these permanently shadowed regions. But with the NASA Lunar Reconnaissance Orbiter, the picture that was mapped out turns out to be more complicated. What you see now, so the permanently shadowed regions are is the light blue speckling that you see, and also some of the wider circles around the big black patches. Those are the permanently shadowed regions. But the more fuzzy light blue patches that you see on this map are places that are essentially hydrogen-rich, and therefore interpreted as water-rich, but are sometimes not necessarily in a permanently shadowed region, and that's a mystery. For example, at the far right, the most far right patch that you see, it's almost purple. It's got so much water, it's got so much hydrogen. Well, that's not in a permanently shadowed region. So how do you have water ice surviving there without it being cold enough? Because even though it's cold on average maybe throughout the year, it's still going to see sunlight at some point, and the water is not going to survive if it's exposed to sunlight. So the interpretation is that some of this water must be buried. And sure enough, this map is a map built by neutron spectrometry, which doesn't just see the surface, but sees whatever hydrogen the surface has all the way down to about 1 meter in the soil, okay, 1 yard. So the thinking is that most of this water ice is buried, but not at great depth, within just a meter or so. And so all you need to do is go to the polar regions of the moon with a shovel, and you're going to expose water ice, which if you could extract would be of huge benefit, because H2O can be split. Well, first of all, you can use it for drinking, so you have a source of hydration now. But you can also split H2O into hydrogen and oxygen, and that's rocket fuel. And so all of a sudden, you have the prospect of even having a gas station on the moon, where you could fly a rocket there, refuel it with hydrogen and oxygen, fly back to the Earth, go back and forth. All of a sudden, you have an economy going with, transportation of cargo and resources being extracted. So, Apollo was just this distant memory of missions to near the equator. And by the way, because the Apollo missions were confined to the equatorial regions, the Earth was never on the horizon. Okay, when you are near the center of the moon, basically, to see the Earth, you sort of have to lean backwards because the Earth is way above you. Okay, just think of a person standing on the moon right in the middle of the moon where you're looking at it. Obviously, you're going to look at that person sort of from the head down. And so similarly, we'll see you only if he or she raises his head all the way back. So this is a typical view of where the Earth is for an Apollo astronaut, but we were going to go to a place where the sun was going to be on the horizon. And that gave rise to the current program, the Artemis program, named after Artemis, the sister of Apollo. Now, Artemis program is born out of, a lot of excitement here, because let's go for the water at the south pole of the moon, where there's more than at the north pole. And let's do that quick because other people might get to it. And so what's happening now essentially is a gold rush to the south pole of the moon, where the gold is not gold, but just water. Okay. Now, there are other resources potentially you could harvest on the moon, but the main thing really that's going to buy down the cost of even getting to the moon is water. So we have the Artemis 1 mission using NASA's new giant rocket, the SLS, which flew only once, but it was a complete success when it flew. One of the most powerful rockets ever built. And this is it launching a capsule that did not go to the moon to land there, but did a fly around the moon and came back. And the capsule was not occupied, so this was an uncrewed mission, but it took place just a couple years ago. And it was a big success. Here's the cabin flying past the moon. The moon is actually upside down, although it doesn't matter much. And it actually reached one of the most distant, the farthest point away from the Earth for any spacecraft intended for a crew. So quite a feat. And what's going to happen soon, although it was supposed to happen back in November of 24, and then it got updated to September 25, and now it's April 26. We're going to send 4 astronauts to do what essentially Bowman, Anders, and Lovell did for the Apollo program with Apollo 8. They're going to go fly by the moon without landing on it, riding on an SLS rocket and a Orion cabin, like we did on Artemis 1. And in fact, Artemis 1 was a rehearsal in some sense for their mission. And when these guys fly, they will reach a point where they will be the humans who have been the most distant from the Earth ever. Okay. So this is in the making very soon. Now, in terms of how we're going to land on the moon, it will be for later missions to do. In fact, the next one. And there are 2 solutions currently retained by NASA or contracted by NASA. The first one that came online was the SpaceX Starship in terms of contracting, and then eventually NASA gave a contract as well to Blue Origin for its Blue Moon Mk2 lander. And so these, of course, compared to Apollo, are completely gigantic and supersized, especially the SpaceX Starship. I mean, imagine landing on the moon on the SpaceX Starship. Now you have to come down from the top of the rocket where your cabin is, because the rest is fuel tanks. You have to come down some sort of a platform, which you can see at the base. It's like one of those window cleaning things, okay, that lowers you to the surface and then back up again. So the scenario with either of these solutions is not good. With Apollo, you could have one giant Saturn rocket send all the hardware that you needed to the surface of the moon and come back, and you could do one mission with a single launch. Here, the scenario is very different. I'm not going to go into a lot of details, but I just want to point out a few things. So you see, you start with this giant rocket, which is going to send into space a giant fuel tank. Here's the giant fuel tank, and by the time it gets into space, it's empty. So you need to launch at least 4, and we're now thinking more than 4, I say we, meaning SpaceX, to refill it. So you're going to have several launches of Starship, that giant rocket that we've been seeing lately, full of fuel, so that by the time they get into space and are partially unfueled, they're going to transfer their fuel over to this giant fuel tank. Once this giant fuel tank is full, you launch a Starship that's actually going to land on the moon, but with nobody on board. Here it is, the last one. It goes into space, and your Starship is going to dock with this fuel tank to refuel. Again, you're not on board. This is all unmanned, uncrewed. Once your Starship that's going to land on the moon is full of fuel, it's going to travel with nobody inside all the way to the moon and park itself in an orbit called NHRO, Near Rectilinear Halo Orbit. It's unnecessary to know what that means, other than the fact that it's going to be an orbit that allows you to stay for a long time over the South Pole. Since we're going to be operating at the South Pole, you want to be in a place where you can see it as long as possible. And one of the things I do not like to see on any chart is loiter. But basically, once you get to the moon, your fully fueled Starship, ready to land on the moon, is just going to wait for the actual crew to launch on the NASA SLS and come and connect with the Starship. The crew will transfer 2 people over to the Starship, 2 very lonely souls, and that Starship will land on the moon. Since there's no refueling, they have to be careful and relaunch with the rest of their fuel into lunar orbit, transfer the 2 people back into the Orion capsule, and then that capsule flies back to the Earth. That's the scenario with Starship. It is far more complicated than Apollo, if you remember how Apollo went down. Okay, lots of failure points. What if the refueling doesn't happen well around the moon? What if the transfer of the crew doesn't happen safely? I mean, you're talking about docking with a Starship now. It's a huge beast. All right. Same problem, essentially, with the Blue Origin scenario. I'm not going to go through this in detail, other than to say that in the Blue Origin scenario, the main difference, really, is that your fuel tanker with fuel goes to lunar orbit, and then you refuel it with your lander once you get to lunar orbit, as opposed to Starship getting refueled in low Earth orbit and flying itself to the moon, to the lunar orbit. But the problem, from my perspective, as much as I love NASA and what it does, and part of me is sort of, non-critical of anything that NASA does, Artemis 3, which is the first human landing after the flyby with Artemis 2, marking our return to the moon, to the surface of the moon. Artemis 3, 4, 5, and 6 are sortie missions. As we land in a different spot again, and there's the claim that we might land in the same place twice, but still, it's not enough forward thinking, and we're just going after something that we're not even sure is there and is extractable. That is sort of the problem. And here is so one is the strategy that you're doing sortie missions again, which will make the program eminently cancelable. But the second thing is, if you look at this map of hydrogen at the south pole of the moon, you can see that there are places where there are higher concentrations of it, like here at Cabeus, here inside Shoemaker crater, and that little spot in the distance we had talked about before. Shoemaker and Cabeus are permanently shadowed regions. Okay? But how much hydrogen is there really in even these most highly concentrated places for hydrogen? Look at the scale down here. The water equivalent hydrogen, in other words, if you were to convert the hydrogen into an equivalent amount of water, it occupies, when it's purple, at the highest concentration, it's only 0.5 weight% of the soil. What does that mean? It means that if you extract 1 metric ton of lunar soil, you're going to get 5 liters of water out of it, 5 kilos. That's the highest concentration, and that's assuming you are 100% efficient in recovering all the water that you extract from the soil. Okay. To fill a Starship, when the Starship launches, the top part of the rocket, the thing that would land on the moon and fly back with astronauts, that thing carries about 1,200 metric tons of fuel. So to refill the Starship with, say, just a ballpark of 1,000 metric tons, you need to basically excavate down to a depth of 1 meter, the equivalent of almost 25 football fields. All right. So to me, this gold rush about the water is completely unreasonable. Because even though we still have a lot that we don't understand about the distribution of the ice, maybe it's concentrated in chunks of iceberg that you could somehow unearth, and because this is in the end a relatively low resolution map, so maybe you don't necessarily have to plow football fields. Maybe you can find giant blobs of it, so that you can access the ice more easily. Extracting the ice, exposing it, is just the first step. Then you have to make sure it doesn't just sublimate, disappear into the vacuum of space. So, as soon as you excavate it, you have to contain it. And then you have to separate it from the dirt, because the rocket's not going to run on any dirt. It has to have very clean hydrogen and oxygen. And of course, you're not going to operate this where you extract it with the temperatures at minus 270 Fahrenheit, because we don't even have machinery that work at those temperatures. We have spacecraft that fly by Pluto, but they don't have moving parts like excavators and scoops and giant wheels. They just spin around with little rocket motors. You're talking about cryo-robotics, robotics that are designed for extreme cold that do not exist. And you know how it is. Moving parts and electronics do not like the cold. If you have a robot that is subject to these kinds of temperatures. So I'm not claiming that none of this is not possible. I'm just saying, what's the alternative? Well, the alternative is to fly the water in from the Earth, the good old-fashioned way. And when you think about it, any single landing of a Starship on the moon can bring in, because that's the landing mass, the payload mass, it can bring in 100 or so metric tons of clean, purified water from Crystal Springs or the Coca-Cola Company, okay? Honestly, you can have, essentially with a Starship landed with just water as the payload, a water tower sitting wherever you want it on the moon, outside of a 50 Kelvin permanently shadowed region. And it's, of course, not really there for you to turn into fuel again, but if you had to, you could. And you would have water that you could use and recycle. And the big question, and of course this would not be free, it would cost, maybe a few $100 million if by the time you have several Starship launches to get you going with one landing on the moon. But when will we have 125 metric tons of clean water sitting at the surface of the moon where we want it in a water tower with a tap at the bottom ready for you to use, if you were to extract it from the south pole of the moon? And to me, it's a big gamble that we are engaging in here with the space program by throwing all our assets in short-term landings at the south pole just in the hopes of finding some water. It gets worse. We know that the ice is not at the surface because A very interesting mission was recently flown called ShadowCam. It's an American camera on board a Korean orbiter, and it would have been completely blinded if it took pictures of any areas that were sunlit, but it was taking pictures of some of these permanently shadowed regions by just using the indirect lighting from the sunlit rim of craters, casting some feeble lighting into the inside of the crater. And we were able, for example, to fill in the topography of Shackleton crater, which is at the south pole of the moon. This thing is 20 kilometers in diameter, so about 15 miles or so in diameter. And we were wondering, would we see glaciers or patches of ice or something that we could tell is ice? We see nothing, even though it is a patch there's a bit of a hydrogen signature there, okay? So you're talking about ice that is not going to be easy for you to just scoop up. You have to dig for it. That's the first piece of bad news. Second piece of bad news is that the south pole of the moon is lunar highlands, very rough terrain. We talked about the seas of the moon and the lunar highlands just earlier. The highlands of the moon are the ancient crust of the moon. They've been pounded by impacts. The terrain is super rough, mountainous, or at the very least very hilly. And that's one thing. We can, with a good rover, probably negotiate the slopes. But look at what the sunlight does if you're not careful. So it's not like you have on the moon elsewhere at lower latitudes 14 days of permanent sunlight followed by 14 days of night. The 14 days of night are a problem, and to survive the lunar night, we might need nuclear power, to power a base. But we've done that before. We had nuclear power in Antarctica, for example, for a base. Here, we are trying to say that we could set up shop there, and as the shadows move around, as the moon rotates around the Earth, as the shadows move around, we can stay clear of the shadows by chasing the sun, essentially, as we go about our road trips, for example. And I find that to be completely super high risk, because what if your rover gets stuck, all of a sudden the shadow is going to sweep in, and now you're going to be caught at 50 degrees Kelvin, minus 270 degrees Fahrenheit, 370 degrees Fahrenheit, in the cold of the moon. So this is what's happening at the pole of the moon this year. It starts on January 1st. You're going to see today click by, and then it's going to go to the end of the year. All right. So plan a road trip here where you're not allowed to loiter, talking about loitering, in darkness. It's super high risk. I mean, a vehicle can break down, your pressurized rover could break down, you might not even have time to fix it because you're going to get stuck in super cold temperatures. Astronauts who are landing on the Artemis mission, of course this is sped up, okay, this whole cycle takes 28 days, but still, when we're talking about landing with astronauts at the South Pole, we're talking about catching one of these patches that are sunlit temporarily and carrying out the mission before the shadows sweep in again. All right, very dangerous, super high risk. And then to make things worse, it's not like astronauts can really enter the permanently shadowed regions. They can't spend more than an hour and a half in them. And most of the ice is actually deep inside some of these permanently shadowed regions, like kilometers in. And so I really question the wisdom of us sending astronauts to the South Pole of the moon without the support of a base, with just sortie missions. This is no Apollo. And it's not like we are shying away from a challenge. President Kennedy said, we choose to go to the moon not because it is easy, but because it is hard. Okay, but this is not hard. This is just really asking for it. Okay, is my point. So why a base? I've spent some time in Antarctica and the Arctic. Those little red dots are places where I've spent a summer or even a year. I've been to medium-sized bases, large bases like McMurdo, small bases like our base in the Arctic. The base is what you do. A base is an infrastructure that allows you to offer shelter, a safe haven for surface explorers. It allows you to repair a vehicle. It allows you to regroup and launch another excursion to where you want to go explore. It's actually what the military do as well to conquer a territory. You set up a fort, a garrison somewhere, and then you fan out from there. This is exactly the same strategy for science in Antarctica. You set up a base, and with a mobility system, vehicles, aircraft, you go to other places that you want to explore, and then you keep going back and forth. That's your logistics base. It's a very proven strategy. Now that we're going back to the moon, we should really do that instead of doing more sortie missions. In Antarctica, the mobility system is largely based at McMurdo. So we have a giant base at a location that is just convenient logistically. It's not the most interesting necessarily in Antarctica, although it turns out to be really interesting. But for science, we really want to be able to roam the whole continent. And for geopolitical reasons, we want to be able to access any part of the continent, including our base at the South Pole. And so for that, you have a range of mobility systems to do that. Same thing with our base in the Arctic at a much smaller scale. We have a small base camp, but it's a base camp. And we use a range of mobility systems, including the ATVs that I love riding in the summer, to roam around Devon Island, where we do our Mars analog work. Okay. Devon Island, by the way, is the largest uninhabited island on Earth, and Houghton Crater is a giant meteorite impact crater that's about the size of Shackleton Crater, okay, 15 miles across or 20 kilometers across. An amazing place. So we did, nevertheless, go through the exercise of let's say you had to. Let's say NASA is not swayable on this, and we really have to set up a base at the South Pole of the moon. Where would you do that? So I went through this exercise in 2021 with a group of other colleagues and students. And so here were the criteria we thought were important. You want a smooth area that's at least 1 kilometer square so that you can expand your base a little bit over time. You want slopes that are less than 3 degrees so that you can, you're not walking on tilted habitats. You want solar illumination to be available at least 75% of the time, because the assumption here is going to use solar power, at one of the high points in this landscape. You want direct-to-earth, DTE, direct-to-earth visibility to be more than 50% of the time. So since the moon wobbles, imagine there's a hill between you and the Earth. Sometimes the hill can hide the Earth, sometimes the hill can expose the Earth. So you want to see the Earth at least half the time directly, okay? And then you want a separation between your landing pad, launch pad, and your base, because these Starship landings are going to kick up a huge amount of dust, and the launches as well. And if you were right there at the same level, you're going to get completely sprayed by all the exhaust ejecta, basically the rocket plume, and what it entrains with the dust, and that's not good. So we want 100 meters separation in elevation and at least a range of up to 2.5 kilometers. Not at least, but up to 2.5 kilometers was deemed to be sort of a good distance, anywhere from 1 kilometer to 2.5 kilometers. And then you want this to be a place from where you can roam beyond. And so we wanted to be able to do a 100-kilometer traverse from that location without encountering slopes more than 20 degrees. Okay. The lunar rover on Apollo was able to go up maximum slopes of 17 degrees. Well, there's the result, okay? And we're not going to go through this in detail, but just to take the first one, Shackleton-Slater. That's a crater where, that's a site where for you to drive to the nearest water-rich PSR, permanently shadowed region, if you can handle slopes of up to 20 degrees, you just have to drive 4.8 kilometers. If you can only handle slopes that are less, like 10 degrees, you have to drive a little farther, 6.7 degrees, so that 6.7 kilometers, so that you can get, in through a ramp that's a little shallower. If you want to see what the average distance it is located at from 5 nearby water-rich, permanently shadowed regions, the average driving distance between you and the ice would be 17.4 kilometers if you can tackle slopes of up to 20 degrees, and 39.2 kilometers, that would be the average driving distance for you to get to ice, within the 5 nearest water-rich, permanently shadowed regions, if you can tackle slopes of only 10 degrees. Okay, so that's how this table works. And only the first 3 really are viable because the others have insane driving distances to get anywhere near water ice. So these are the top 3 candidates if you really had to set up a base at the moon. But None of these are really good for lunar exploration sites. They are lethal because of the varying shadows of the low temperatures and the low visibility. I mean, when you're in darkness, you can't even drive unless you have floodlights. You have extreme highland terrain that's steep and rough. You have spotty direct-to-Earth visibility, and you have poor access to other regions of the moon. So these might be good places if you can set up a mine there, or an observatory. In other words, where your activity is really centered on where you are, and you don't have to really roam around. But if you want an exploration base, these are not good places. So we published our table in 2021 of the areas where there were some reasonable candidates. And guess what? When NASA came out about a year later with its map of where Artemis 3 might go, you will recognize that it looks a lot like our map, which we were very happy about. It meant that, we did a good job, I guess. So this is, at the bottom, the landing regions that are being considered for NASA's first return to the moon with humans, the Artemis 3 mission, which is currently scheduled for something like 2028. Now, in the meantime, we are accelerating our exploration of the south pole of the moon with robotic missions. In my view, we're not really doing enough. China, meanwhile, is planning its own human mission to the moon. It has actually hardware built already, but here are some diagrams that show things clearly. A command module that's sort of like the Apollo command module, and then a lander on top of a upper stage thruster. This is sort of something that was captured on a Chinese network, Chinese news network. And you can see that the lander does not have, like the Apollo lander, a descent stage that ends up staying on the moon and an ascent stage that sort of, just cuts your losses and takes you up with just the ascent fuel tanks and the smaller cabin. Here, the whole thing lands on the moon and the whole thing takes off again. So this implies that China is planning to do refueling and plans to reuse this vessel as opposed to discarding half of it every time it lands somewhere. Okay, so it's a very interesting strategy, which of course resembles what we're planning to do with Starship and Blue Moon Mk2. Where might China land? Well, rumor has it that they might land at Tycho, which is the brightest impact crater on the near side of the moon with a giant network of ejector rays. It's bright because it's very fresh. We think it's only 100 million years, 108 million years in age, which would seem probably old to all of us, but in a relative sense, it's a very recent event on the moon. In the middle of Tycho, you have a beautiful hill. Here it is. It's a central uplift. So think of it as basement rocks that have been thrusted upwards by some sort of a rebound effect from the impact. Definitely a magnificent site, although not necessarily very convenient to explore from, because you have to get out of the rim. You have to get over the rim of Tycho to go anywhere, and the rim is pretty steep because it's a very fresh crater. Okay. So, where would you set up a base on the moon? There are lots of interesting, famous places: Crater Kepler, Crater Copernicus, Crater Eratosthenes, Crater Aristarchus, Plato. In the southern hemisphere, we have Tycho, and then we have Clavius. Well, here is roughly where you should do what on the moon. The polar regions really should be off limits for a base unless you actually find a place where you can extract water and mine it, in which case you set up a mine there. That's not an exploration base, that's a mining operation. And we won't know if that's even going to be economically viable until we actually find a good place to do that. So I see this as something that we could do in the future once we know where to set up shop at the south pole of the moon or even at the north pole. In the meantime, to set up a logistics base where you would have a facility from where you can roam around and explore the rest of the moon, including the polar regions, you should do that on the lunar near side because that's where you can communicate with the Earth easily. And it's also much easier for you to plan the road trips. And I think from a public outreach and education standpoint, it's a lot better to know where on the moon your astronauts are and your bases than if it was hiding on the far side. The far side, however, is attractive if you want to set up an astronomical observatory, for example, a radio telescope that would be completely shielded from the radio noise of the Earth and listen quietly at the rest of the universe. You would set that up on the far side of the moon. So after some probing and surveying, we narrowed our searches to several candidates, but I'm going to present one of those to you today. And it's, at this point, my personal favorite. It's Clavius crater. Clavius crater is an old crater, and there are other craters superimposed on it, including Rutherford and Porter. But you can already see how from Clavius, you can see that, first of all, the high ground on this map, this is a topographic map, so the high ground on this map is gray in color. And you can see that if you're trying to access the South Pole from Clavius, you essentially have a wall of high elevation terrain, except that there's a corridor running right there down the middle of this slide. And that corridor is very important because, as it turns out, it's a very good, smooth, low-slope access route to the South Pole of the moon. So by being based at Clavius, even though you're not at the South Pole, you could reasonably drive there with a relatively straight shot. Okay. But let's talk about Clavius a little more. It's at 58 degrees south. Okay. The diameter is 231 kilometers. That's roughly the distance between Washington, D.C. and Philadelphia. The depth is 3.5 kilometers. It's Nectarian in age, so one of the earliest periods of the history of the moon, 3.92 to 3.85 billion years. Okay, and you can see that the crater, we're talking about the big one here, not any one of the small ones. The big one is relatively eroded, and you don't have the sharp rims like you have at at Tycho, for example. The floor is not entirely flat. This is a topographic map of the floor of Clavius. In fact, the western part and the eastern part are lower in elevation, and there's some sort of a ridge running down the middle, north-south, and there's a difference in elevation of about 700 meters between the red and the purple here. Okay, so not a huge, not something that you would even perceive once you are on the ground, but it's something that should be noted. When you're at crater JA, for example, you might not be able to see the rim on the far side very well of Clavius. So let's talk about Clavius's history, okay? And I'm not going to bore you, I hope, with too much geological details, but why is this site even interesting if you wanted to explore the moon? Why go there? Why not somewhere else? Well, let's start with the origin of the moon. So the moon starts with the collision of a Mars-sized object with the proto-Earth. The Earth was only 90%, 95% of its size today at the time of this impact. And we're looking at something that happened about 4.59 billion years ago. Okay. So at that point, the Earth had no moon. The Earth wasn't even quite its size yet. Once again, we call it the proto-Earth. And one day, and now that I think about it, I think it was a Wednesday, a giant object comes in the size of Mars, and this is what happens as modeled by my colleague Robin Canup. Okay. So the Earth is completely melted. The impactor dumps a huge chunk of itself into the Earth, so the Earth grows in size, and the remaining gets flung into orbit around the Earth into a giant disk of debris, some of it continuing to fall into the Earth, some of it eventually coalescing into the moon in orbit around the Earth. No, that's not going to be the moon. That gets pulled in as well. So these models, of course, you can vary the conditions and you get different outcomes, but eventually we get a moon. And so very early on, the moon, 4.5 billion years ago, shortly after its formation, was much closer to the Earth. We're showing it here when the crust had just essentially solidified, more or less. And very quickly, it started moving out as the Earth was spinning down. The Earth was spinning at about 5 hours per day at the time. With the moon moving out, the Earth started slowing dramatically in its spin rate. You can see where it is now, the moon, and in 4 billion years from now, it's going to be a little farther out. So at this point, I think I've mentioned this to you or to the other group before, the moon is receding at a rate of about 1.5 inches per year. So that's the rate at which your fingernails grow. I call that the rule of thumb. Okay. So this is, of course, too detailed for you to even care to look at, but just know that here is the formation of the Earth at the very beginning of this red bar. Then you have this little yellow segment here, which is the giant impact between the Earth and the moon. Then there's a phase where there's a magma ocean, both on the Earth and on the moon, but this is really for the moon. Eventually, the crust of the moon forms. And then, one of the first early basins that punches through the crust is the South Pole Aitken Basin, which, remember, we talked about at the beginning of this talk, on the far side of the moon, near the South Pole. So the South Pole Aitken Basin is interesting because it might have excavated material from the inside of the moon dating back to that time when the moon's crust had just freshly formed. And then eventually, Clavius forms here in the Nectarian period, a very narrow time frame towards the end of the pre-Nectarian. Eventually, there's an epoch called the Imbrian, when impacts were still fast and furious and very intense. And then eventually, but it was mostly intense here during the Nectarian. And then eventually, things died down. You had a relatively calm period during the Aristotelian, and one that's really even calmer and lacking action, which is called the Copernican. That's the last 1.1 billion years of the history of the Earth. Tycho crater formed near the end of the Copernican at this, on this time scale. So, there you go. The Clavius crater forms in the Nectarian during the heavy bombardment about 400 million years after the crust of the moon solidified. Then you had the Porter crater, which formed in roughly the same time frame, but obviously after Clavius. It also, at the same time, there was some wrinkling on the floor of Clavius because we think the floor sagged downwards a little bit and got compressed. Then this is, by the way, work that I've been putting together with a student of mine who's at the University of Colorado in Boulder. She's a sophomore only, and her name is Erin Sampson. So Erin and I have been working on the geology of Clavius here for the past few months. Then came the Imbrian period, where there was still some pretty intense bombardment. So a number of these craters that are pretty worn out were formed at that time in blue. Then you had an episode of apparently volcanic eruptions. That's sort of interesting, and they actually used some of the cracks that were formed up near Porter, some of the wrinkle ridges, to come to the surface. And here are some of these volcanoes that you can sort of see on the floor of Clavius crater. So very interesting geology. Things are happening throughout this history since its formation. And then came the Eratosthenian, where things calmed down dramatically in terms of impact rate, but nevertheless, two big impacts, crater D and crater L, Clavius D and L, took place. Then, in the modern era, within the last 1.1 billion years, Rutherford impact formed, a very crisp-looking, still today, impact crater with rays and lots of ejecta associated with it. You can still see it. The Copernican, that's depicted in yellow, is also the time frame when the Tycho crater formed, but Rutherford formed before Tycho, and then Tycho formed north of Clavius, that impact, and it essentially showered Clavius with one of its bright rays of ejecta. And so the next slide here shows this band cutting across Clavius. That's essentially stuff ejected from Tycho crater when it formed 108 million years ago. Okay. So the point of all this is just to show that there's a lot going on here. You go to this place, you can study the early history of the moon, all the way to the recent times. And so this is a map that Erin Sampson and I just published. And we're very excited about this because it's a map that's really highlighting the geologic features for lunar science and human exploration. Okay, if humans went there, this is where we would go. So there's a little more to it than that. Just 2 years ago, or is it 3 now, water was found at Clavius. Now that is very bizarre. Water, the water molecule, we're not talking about detecting hydrogen now, we're talking about detecting the water molecule at the surface of the moon, which is borderline incomprehensible, but we think it's somehow tied to the grains at the surface, and so it's not that like there's a lot, but nevertheless in detectable amounts, and more so in Clavius than in surrounding terrain. And this plot here in the middle just shows you that in the surrounding terrain, the curve in black, you don't see major spikes near 6 microns, which would be indicative of water being present, but where it says 58 degrees 0.8 south, the red plot, which is inside Clavius, you see a whopping signal due to water being detected. And the amount of water is nothing you could extract to turn into fuel, but it's nevertheless really interesting. And the big question, of course, is where does it come from? Why is there a concentration of water inside Clavius? Maybe there's a source of it that is unknown in the terrain, or maybe in some of its shadowed areas. So Pete Schultz at Brown University and his colleague, I forget the first name, but its last name is Lee, no relation. It's not even the same spelling. But Schultz and Lee proposed that it's the Rutherford impact, this very recent impact that is sort of sitting on the rim of Clavius. They suggest that the Rutherford impact was formed by a water-rich asteroid or comet. And it's that impact that essentially dumped a lot of water onto the floor of Clavius. And in fact, they show evidence for that by saying that this green stuff is possibly hydrated minerals on the floor of Clavius. Okay? And it matches essentially an ejecta ray, if you will, from the Rutherford impact. So this is not widely accepted, but it's an interesting idea that the water that we're seeing there concentrated in Clavius came from the impact at this site of a water-rich comet or asteroid. And then this map shows you that even at Clavius, even though you're not at the south pole of the moon, there are nevertheless permanently shadowed regions, except that they're much smaller, and they are essentially at the base of the rims of impact craters on their northern inside, on the northern side inside the craters. You are right there below the wall, if you will, of the crater, and you are never going to see the sun in those locations. And a paper was published just 2 years ago by Schmidt and Petro. This is no other than Harrison Jack Schmitt, who was the scientist astronaut on Apollo 17. Jack Schmitt came up with this paper and said, hey, we should really go to a place like Clavius L, that little crater on the left there on the western side of Clavius, because it has a relatively large permanently shadowed region. And Jack Schmitt himself thinks that it's unreasonable to send astronauts to the south pole of the moon right now. He thinks that we should go to a place that's a lot more benign, like Clavius, to practice doing exploration of permanently shadowed regions. And once we've got this whole shadow region thing nailed, then we can go venture to interesting places at the South Pole. So I don't want to exceed my time, but I'll just keep running. Another interesting finding that I made with my students, Aaron Sampson in 2025, so this just got published, as well as with Daniel Sykes. Daniel is a senior at the University of Kansas in astrobiology and planetary science. So Daniel mapped some caves on the floor of Rutherford, and so did we find some caves on the floor on the ejecta blanket of Rutherford with Aaron. So here are some of these caves. I just wanted to show them to you. Okay, cave entrances on the floor of the crater and on the ejecta blanket. So by going there, you could access caves. And this, to me, would be a really fascinating thing. So I'm going to wrap up here in just a couple of minutes. Caves are fascinating on the moon because that's really where you want to go once you go to Mars. When we go to Mars, we want to look for life on Mars. And one of the best places to find life at this point that's still alive is inside caves. It's underground on Mars, not at the surface. And the reason why you want to find life that's alive is because it's only that way that you could do genetic analysis on that life form, protein analysis, to do biochemistry on it, to establish that it's really alien from Earth life. If all you find is a fossil, you can't even tell if it's not just Earth life that got exported to Mars and somehow picked up there. Okay. So our search for life on Mars really has to target living life, and to do that, we want to go underground and therefore into caves. Here's a map of caves on Mars. They're all over the place. In the Tharsis and Elysium region, those are the two major volcanic provinces of Mars, and of course they are lava tubes mostly. Recently, I went into a lava tube with spacesuit engineers from Collins Aerospace. They hold the heritage of making the Apollo moon suit and the Space Shuttle and Space Station EMU suit. This was the first study of caving with a spacesuit manufacturer ever. And we did this in Oregon at Skylight Cave. You can see where we think we should position our LED lights and why we should also have a hockey goalie face mask to not bump our visor into the walls of the cave. And here's our lighting configuration. So the point is, caving is being studied as something that we could be doing soon on the moon and Mars, and therefore we should go to a place where there are caves to be accessed. So where would you set up this base at Clavius? Well, here's a good spot. And of course, this is not final. We would have to do a robotic reconnaissance mission to assess the terrain properties, the physical properties of the ground, the geotechnical properties to set up a habitat. But this is a candidate where we could go do this reconnaissance mission. It's a very interesting place because from there you can drive into Rutherford. You can also drive towards the South Pole. And I was mentioning to you this corridor that could take you to the South Pole. Here it is. It's a road that would never exceed 13 degrees in slope, okay, which is pretty viable all the way to the South Pole. So, of course, it's a long distance to drive. It's a few hundred kilometers. But that's not something we would do on the first mission to Clavius. But it's something that over time, by flagging the route, we could establish a route and get there frequently. And just to compare what we're doing in Antarctica, there's a road that we've established, that the US program has established, not me, to drive from McMurdo to the South Pole every summer to transport supplies and resupply the South Pole station. So you can see that this same route that we are talking about from Clavius to the South Pole of the Moon, shown here at the same scale, is not anything much different from what we're doing at the South Pole in Antarctica. So I'll just end with this. 2001, A Space Odyssey, curiously, had picked Clavius as the site for its base. And at the time, you can say that Arthur C. Clarke had a lot of foresight. Yes, he did have a lot of foresight, but there's no way he knew all these details that we're now finding out about the geology of the place because he didn't have the data. So he just had a good intuition that a big, flat, ancient crater in the southern hemisphere of the moon would be a good idea. But sure enough, it's turning into, I think, a really exciting place to go. The Earth is too low on the horizon there because you're not at the South Pole. You're actually at 60 degrees south, so the Earth is higher in the sky. And I'll correct that in a second, but it's an amazing coincidence. But this movie is really, if you haven't seen it in a long time or have never seen it, brace yourself, of course, but go see it again. It's an amazing masterpiece of our future in space. And this movie had it right. You set up a base, and when you find something interesting, in this case, a monolith, but in our case, maybe a place where you could mine water, then you use a mobility system to go there. You can use a hopper or a rover that rolls on the terrain. And here is where you set up a mining operation, okay? So once we know, if we find a place where we could extract water economically, and once we know where that's going to be, you set up a mining operation which can be supplied from the base. But you don't start with a base at the South Pole of the Moon or sortie missions to find the ice. That's not how you do it. So I'll just end with this slide, which is actually my last slide. It's from the movie, of course, but the Earth is now properly positioned in the sky at Clavius. Thank you.
Okay,
So
I'm
sorry, I ran
I'm
long.
gonna ask him what you asked the kid, because today he asked the kids, after he told them all this stuff, how many people want to go to Mars? And they're all, so how many people want to go to Clavius?
Let's see a show of hands. Don't be shy.
Yeah, show of hands. How many people want to
Assume
go to
immortality.
Clavius?
How many here would be
Exactly.
interested in going to Clavius? Okay, great.
Okay, obviously, we went over some, but so just a couple of questions if someone is, Nick? Okay. All right, you ready? I'm going to throw this at you.
Good catch.
Thank you. I was just wondering, given the status of Clavius and their current moon missions, do you think that we'll be able to design a base here on Earth that will be able to ship to both the moon and multiple other planets that can adapt to multiple environments as we have done so on Earth? Because you have to take into account the actual weather of each planet when you arrive there.
Yeah. So the thermal conditions are really the crux of it, and because they're quite different on the moon and on Mars, you could possibly use the same basic design, but you would have to adapt the whole insulation and thermal control to the local environment. But fundamentally, a base like that on the moon, if it's at Clavius, you can't just rely on solar power for one thing. I mean, solar power is a bad solution anyway because of all the Starship launches and landings and your activity. The solar panels are going to get coated in dust. So you really want nuclear power. And of course, that's not a very popular word in space, up until now at least. And we're now, I think, seeing some solutions for nuclear power on the moon that could be a peaceful use of it, of course. But that would be the only solution to power a base and then survive the lunar night, which is 14 days of darkness. And that's sort of the way to go. So I think we should make a big push for nuclear power. But that's an example of something that, we should develop for the moon so that it's available for Mars, because we'll need that for Mars. So there are lots of commonalities in solutions, yes.
Okay, we have one more question here in the back.
Yeah, sorry I ran long. Thank you for staying.
Testing. Okay. So before we go disrupt an over billion-year-old site, what are critical resources that we don't already have on Earth that we're looking for?
So that's a good point. I mean, I don't subscribe to the idea that we're going to the moon to somehow bring resources back to the Earth. At least that's not what I feel is the driver. I personally feel that the driver is to explore. And of course, in all exploration, there's always a geopolitical dimension to it. So for example, I spent a lot of time in Antarctica, but I do science there. But we're not in Antarctica for science. The United States does not pay the NSF or give the NSF a budget of about $2 billion a year because of science in Antarctica. It's because being there serves the national interest. The Antarctic continent is a geopolitical chessboard, and there are other players there. You have to be there. You have to be part of that. You have to be present. And down the road, there might be resources to be had. And for now, it's just very important to just showcase your presence. And it's not a surprise that the United States spends money to remain present at the South Pole itself, which is a very strategic location, and supplies McMurdo, which is a huge base. Now, once you've committed to being there, what are you going to do? So science is what's going to dominate your activity, but it's not the motivation why you're there. And it's really important to understand that. So to me, we're pushing for the moon because we can't just let China, for example, go about its business without us being present. And it's the same thing for Mars. I think fundamentally, we haven't been to Mars yet because there hasn't been any rush or any threat. But now that people are already making their ambitions known, I think it's going to become very important for the United States to sort of be a player in this. So this is a bit of a cynical view of why we go into space with people, but it benefits science as well. And I think to me Mars is very attractive because of the search for life. we might find the first example of an alien form of life on Mars, and it's really worth the quest. If it, at the same time, allows us to beat some competing nation in a race, so be it. Yep.
All right, y'all, we'd like to thank Dr. Lee for being here today. Thank you so much.